Welcome to this video, and we are going to calculate here the moment of inertia of a solid cone, okay, about the z-axis. So it's the axis of symmetry of the cone. Again, the idea, if you have been watching the previous derivations we made for moments of inertia of various solid bodies, the idea is always to select an element. In this case, if we cut a very thin slice of the cone, it's going to be a disk, okay? And then we are going to calculate the moment of inertia of this disk and then integrate to generate the whole symmetry or structure of the cone. So you can see that the disk we are having here of thickness dz, we can calculate its moment of inertia. We know its moment of inertia, by the way, it's just half mr squared. We derived this in a previous video. I'm going to leave the link somewhere up here or up there, so you can go and watch this if you want to know how this is derived, and then get back to this video. So let's define the mass per unit volume of this cone. Let's call it rho. So rho is the mass of the cone, m, all about the volume of the cone. The volume of a cone, that's just 1/3 pi radius squared times the height h. But then we can also write this mass per unit volume as a function of the mass of the element. So that's going to be dm divided by the volume of the element. In this case, the element is a disk that has a thickness dz. So that's just the area of the disk, which is pi small r squared times its thickness dz. If we simplify this, we can get the expression of dm. That's just going to be 3m divided by, so we have h, so 3m r squared divided by h, and then dz. I hope that's correct. Yeah, I think that's fine. So 3m squared h dz. Okay, I think that's fine. So then the moment of inertia of the cone about the z-axis is going to be the integral of the moment of inertia of the element. In this case, it's just the moment of inertia of a disk. So that's half times the mass of the disk, dm, times r squared. And we perform this integral over the mass of the disk. Okay? So we can replace dm here. That's going to be half times 3m on h times, we have an r squared here and we have another r squared here, so that makes r to the power 4, and then dz. And we need to integrate this over z. So you can notice that we have two variables. We have z and we have r. So in order to be able to perform this integral, we need a relationship. We need to establish a relationship between the two. And if you look carefully on this diagram, you're going to notice that we have two similar triangles. So we have this smaller one and we have this big one, this bigger one. So if you want, I can zoom in a little. So we have something like that. Okay, so this one is z, this one is r. The bigger triangle has sides h and capital R. Hope you're able to see that. Okay. Then put that there. We can notice that ratio of the sides of similar triangles are the same. So R on capital R is just small z on h. So we can replace small r here. And that's going to be the integral of half times 3m on h times that's r over h z all squared, no, to the power 4 times dz. Okay? Then z, the boundaries of integration has to go from 0 to h. Okay, we need to move this disk from 0 to h in order to generate the whole volume of the cylinder. Okay, let's simplify this. We're going to have Iz as, let's bring out the constants. We have 3m on 2h. We have r to the power 4 on h to the power 4, and we're going to have the integral from 0 to h of z to the power 4 dz. Okay, the rest are just constants. So that gives us 3m on 2h, r4 on h4, and z to the power 5 on 5. We integrate this from 0 to h. If we apply that, we're going to have 3m on 2h, r4 on h4, and h5 on 5. Okay? If you want to simplify this, we can notice that we are going to have an h5 here that's going to cancel this one. Okay? And looks like there's an r squared that is missing. Okay, yeah, I think I omitted an r squared here. Yeah, so here there was supposed to be a capital R squared from here. Sorry for that, I omitted it, and I just realized it. So here I need to have an R squared. Let us just add it. Here I also need to have an R squared. Okay. And here I'm going to have, let me just add 1 over R squared everywhere so that we can compensate 1 over R squared. And here we add a 1 over R squared. Okay, so this is an 1 over R squared that I omitted. Sorry for that. So this 1 over R squared would cancel with this one. And at the end, we're going to have Iz as, so that's 3, 10. So 3 on 10, mr squared. Okay, and that's the moment of inertia of a solid cone about the axis of symmetry of the cone. Hope that's clear.